after learning the concept of improper integrals and how to evaluate improper integrals, before considering additional examples, let us have some exercises on how to recognize improper integral. So in the given examples here, or in the given definite integrals, we will determine if the integral is improper, and we have to state the reason why or why not. Okay, in the first example, or in the first definite integral, the integral of the differential of x over 5x minus 3 from the lower limit 0 to the upper limit 1, if we do not know how to recognize improper integral, then we will simply evaluate the definite integral without knowing whether the given integral is improper or not. Okay, now since we are given a rational integrand, no, then the denominator, of course, is critical. The denominator cannot be 0. And we have, if we will determine the value of x that will make the denominator 0, we simply equate 5x minus 3 to 0. And if we will solve for x, then x is equal to 3 over 5. And since we are considering the lower limit 0 and upper limit 1, then we are considering the closed interval from 0 to 1. Okay, and the value of x that will make the denominator 0, which is x equals 3 over 5. Okay, sorry, it should be 3 over 5. Okay, so this should be 3 over 5. Sorry for that. Okay, and we can see that the value of x, which is 3 over 5, is within the interval. So that will mean that from the lower limit 0 to the upper limit 1, okay, there is a point of discontinuity. There is a vertical asymptote, x is equal to 3 over 5. Hence, the given function, or the integrand 1 over 5x minus 3, is not continuous within the interval from 0 to 1, from the lower limit 0 to the upper limit 1. Okay, hence, we consider the integral of differential of x over 5x minus 3 as an improper integral. Okay, now what about the second one? We have the integral of 2x minus 5 divided by x squared minus 5x plus 6. Okay, and we are going to evaluate the integral from the lower limit 0 to the upper limit 1. Okay, so here we are considering the lower limit 0 and the upper limit 1 within the interval from 0 to 1, and we have to determine whether the given integrand, the given function 2x minus 5 over x squared minus 5x plus 6 is continuous within the interval. Now, we can do so if we will equate the denominator to 0 and determine the critical values of x, the values of x that will make the denominator 0. So if we will equate the denominator x squared minus 5x plus 6 to 0, okay, and looking at the quadratic function x squared minus 5x plus 6, now this can be factored as x minus 2, x minus 3, okay, then equating this to 0, and equating each linear factor to 0 will give us x minus 2 equals 0. Hence, we have x is equal to 2, and equating the linear factor x minus 3 to 0 will give us x is equal to 3. Okay, the values of x that makes the denominator 0 are x is equal to 2 and x is equal to 3. And we can see that it is outside the closed interval from 0 to 1. It is outside, okay, the lower limit 0, upper limit 1. Hence, we can say that the given integral is not an improper integral. Now, of course, example number 3, the definite integral of sine of x over 4 plus x squared times the differential of x from the lower limit of integration negative infinity to the upper limit infinity is obviously an improper integral since the lower limit and the upper limit increases without bound. Okay, hence we have an improper integral. So if we are given a rational integrand, no, we have to determine whether the given integrand is continuous within the limits of integration, from the lower limit of integration to the upper limit of integration. And if the critical value of x, that is, if the value of x that will make the denominator 0 is within the interval, then there is discontinuity on the interval. Okay, there is discontinuity on the closed interval. Hence, we can consider that as an improper integral. Okay, so with that, we can now consider some additional examples. Okay, so we will consider evaluating y e raised to 4y dy from negative infinity to 0. And you can see that the lower limit of integration is infinite. Hence, we can say that the given integral is improper. Okay, and using the definition of improper integral, then the integral of y e raised to 4y dy from the lower limit negative infinity to the upper limit 0 by definition is equal to the limit of the integral. Okay, we can replace negative infinity by a. So lower limit is a and the upper limit is 0. Okay, integral of y e raised to 4y times the differential of y, and limit will be, okay, the limit will be as a approaches negative infinity. Okay, so by definition, the integral is the limit as a decreases without bound of the integral of y e raised to 4y dy from the lower limit a to the upper limit 0. Of course, before evaluating the limit, we need to evaluate the integral of y e raised to 4y dy from a to 0. And we can evaluate the integral by parts. Okay, now since we have algebraic and exponential in the integrand, no, we can follow the acronym LIATE. Okay, so if we will follow the acronym LIATE, we have algebraic and exponential, and the algebraic part, okay, comes before the exponential part. Therefore, you will take the algebraic part. So in here, we will let u is equal to, okay, let me write it here, u is equal to the algebraic part y, and the remaining is the differential of v. And if u is equal to y, then getting the differential of both sides of the equation will give us du is equal to the differential of y. And since dv is e raised to 4y times the differential of y, then integrating both sides will give us v. Of course, the integral of the differential of v is v. okay? And this is equal to the integral of the right member, okay, integral of e raised to 4y dy. And if we will evaluate the right member using the formula integral of e raised to u du, then u is 4y and the differential is 4 dy. Hence, there is a correction factor 1 over 4. Therefore, v is 1 over 4 e raised to 4y. Okay, and if we are going to use integration by parts, then we follow the formula that the integral of u times the differential of v is equal to uv minus the integral of v du. Okay, so by parts, the integral is equal to the limit as a approaches negative infinity of, okay, we have uv, okay, u is y and v is 1/4 e raised to 4y. So multiplying will give us 1 over 4 times y times e raised to 4y, okay, minus the integral of v du, okay. V is 1 over 4 e raised to 4y and du is dy. So this will give us the integral of 1 over 4. We can write 1 over 4 before the integral sign, e raised to 4y times the differential of y. Okay, of course, this must be evaluated from a to 0. Okay, and this integral will be evaluated also from the lower limit a to the upper limit 0. Okay, before evaluating, then we try to, before evaluating rather the limit as a decreases without bound, let us try first to evaluate the integral of v du, which is the integral of e raised to 4y dy, okay, to be evaluated from a to 0. Of course, if we will evaluate this, there is a correction factor 1 over 4 again. So this will give us limit as a decreases without bound of 1 over 4y e raised to 4y, okay, minus, okay, with the correction factor 1 over 4, 1 over 4 times 1 over 4 is 1 over 16, and the integral is e raised to 4y, and this must be evaluated from the lower limit a to the upper limit 0. Okay, so evaluating the indefinite integral within the limits of integration gives us the limit as a decreases without bound of, okay, the value of the indefinite integral at the upper limit 0 will give us 1 over 4 times 0 times e raised to 4 times 0 minus 1 over 16 e raised to 4 times 0, okay, then minus the value of the indefinite integral at the lower limit a. So this will give us 1 over 4 a e raised to 4a minus 1 over 16 e raised to 4a, okay? And this will give us limit as a decreases without bound of course, 1 over 4 times 0 times e to the 0, although e to the 0 is 1, will give us 0 since one of the factors is 0. Now, e to the 0 is 1. Okay, so 0 is 1. So times 1 over 16 will give us minus 1 over 16. Okay, and wait, let me write bracket here. Okay, so this will give us limit of 0 minus 1 over 16, which is the value of the indefinite integral at the upper limit 0. Now minus the value of the indefinite integral at the upper limit, at the lower limit rather, at the lower limit a. So we will have 1 over 4 a e raised to 4a minus 1 over 16 e raised to 4a, okay, close. Okay, so if we are going to evaluate the limit as a decreases without bound, of course, 0 minus 1 over 16 is a constant, therefore the limit is the constant itself, negative 1 over 16. Okay, minus, okay, this gives us 1 over 4a e raised to 4a. Now, if we will evaluate the limit as a decreases without bound, this will be e raised to negative infinity. Now, if we are going to bring this down, then the limit as a decreases without bound will be equal to 0. Okay, similarly with this, okay, we will have e raised to negative infinity. So this will also give us 0. Okay, if we will bring this in the denominator, if the denominator is increasing and the numerator is constant, then that will give us 0. So this expression is equal to 0. Therefore, the integral, the improper integral, is negative 1 over 16. Now, since the limit gives us a fixed value, okay, a specific value, then we can say that the integral of y e raised to 4y times the differential of y from negative infinity to 0 is convergent since the limit exists. Okay, take note that if the limit exists, now we can say that the improper integral is convergent, but if the limit does not exist, then the improper integral is divergent. Okay, this time we are going to consider evaluating the integral of 4 dx over x squared plus 16 from negative infinity to infinity. Of course, it is actually pretty obvious that the integral is improper since both the lower limit and the upper limit are infinite. So if we are going to use the definition, then the integral of 4 dx over x squared plus 16 from negative infinity to positive infinity is equal to the sum of the integrals, okay, 4 times the differential of x over x squared plus 16 from negative infinity to 0. Okay, we can let c is equal to 0. Okay, plus the integral of 4 dx over x squared plus 16 from 0 to positive infinity. That is applying the property of definite integrals. That if we have the integral from a to b, we can express it as sum of integrals, okay, from a to c plus the integral from c to b. And using the definition of improper integrals, the integral of 4 dx over x squared plus 16 from minus infinity to 0 is equal to the limit as a approaches negative infinity of the integral of 4 times the differential of x over x squared plus 16. Okay, negative infinity will be replaced by a, and the upper limit is 0. Then the second integral, the integral of 4 dx over x squared plus 16 from 0 to infinity, by definition is equal to the limit as b increases without bound, as b approaches positive infinity, of the integral from 0. Okay, the upper limit infinity will be replaced by b, okay, 4 dx over x squared plus 16. Of course, before evaluating the limit, okay, we are going to evaluate the definite integrals. Okay, integral of 4 dx over x squared plus 16 from a to 0, and the integral of 4 dx over x squared plus 16 from 0 to b. Now, in both integrals, no, both integrals rather leads to arctangent. Okay, we can have the form du over u squared plus a squared, in which we are going to consider a squared is equal to 16, so that a is equal to 4 by getting the square root of both sides of the equation. And we will let u squared is equal to x squared. Getting the square root of both sides will give us u is equal to x. And getting the differential of both sides will give us du is equal to the differential of x. Of course, the numerator is the differential of x, no? Which is exactly equal to the differential of u. So we can just write 4 before the integral sign. Hence, we can write this as limit as a approaches negative infinity. Okay, we may write 4 before the integral sign, so we will have 4 times the integral of dx over x squared plus 16, which leads to logarithm, is exactly in the form the integral of du over u squared plus a squared. But of course, it leads to arctan, which is in which the integral is equal to 1 over a, okay, times arctan of u over a. Okay, so a is equal to 4. Okay, so we will have 1 over 4 arctan of u over a. Of course, u is x over 4. Okay, then plus the limit as b increases without bound of, okay, we have 4 times the integral of dx over x squared plus 16, of course, leads to arctan. Okay, we have 1 over 4 times arctan of x over 4. Okay, this will be evaluated from a to b, from a to 0. Okay, and this one must be evaluated from 0 to b. Okay, so evaluating the resulting integrals, no, from the lower limit to the upper limit, then let me first do some simplification here. Okay, 4 times 1 over 4 will give us 1. Same goes here. 4 times 1 over 4 is equal to 1. Okay, therefore, this gives us the limit as a decreases without bound of arctangent of x over 4 to be evaluated from the lower limit a to the upper limit 0 plus the limit as b increases without bound of arctangent of x over 4 to be evaluated from the lower limit 0 to the upper limit b. Okay, hence we have a limit as a increases without bound of. Now, arctangent of x over 4 when x is equal to 0 is arctangent of 0. Okay, minus arctangent of x over 4 when x is equal to the lower limit a is arctangent of a over 4. Okay, then plus the limit as b increases without bound of. Okay, when x is equal to the upper limit b will give us arctangent of b over 4 minus the value of arctangent of x over 4 when x is equal to 0 is arctangent of 0 over 4, and of course 0 over 4 is 0. Now, arctangent of 0 is 0. So here, this will be 0. This will also be 0. Okay, and if we are going to evaluate the limit as a decreases without bound, then arctangent of a over 4, if a decreases without bound, okay, will approach negative pi over 2. Okay, so we will have limit of arctangent of 0. Since arctangent of 0 is 0, it is a constant, will give us 0 minus negative pi over 2. Okay, since a decreases without bound. Okay, note that if we will recall our trigonometry, if we will consider the tangent function, okay, if this is the y-axis and this is the x-axis, okay, if this is pi over 2 and we have negative pi over 2, take note the tangent function is not defined at pi over 2 and negative pi over 2. Okay, now the tangent function, tangent of x will increase without bound. Of course, tangent of 0 is equal to 0. And this will increase without bound as x approaches pi over 2. Okay, while if x approaches negative pi over 2, it decreases without bound. Okay, therefore, arctangent of a over 4, if a decreases without bound, will approach negative pi over 2. So this is it. Okay, then we have a plus the limit of arctangent of b over 4 as b increases without bound. So if this increases without bound, then okay, the value will approach pi over 2. So the limit of arctangent of b over 4 as b increases without bound will give us pi over 2 minus, of course, arctangent of 0 is 0. So this will give us 0. Hence, we will have negative of negative pi over 2 is positive pi over 2 plus pi over 2. And pi over 2 plus pi over 2, of course, is pi. Therefore, we can now say that the integral of 4 dx divided by x squared plus 16 from the lower limit negative infinity to the upper limit infinity is convergent since the limit is pi. This is convergent. Okay, so this is the second additional example. This time, if we will consider evaluating the integral of dx over x times x plus 4 from the lower limit 1 to the upper limit infinity. Of course, since the integrand is rational and we have linear factors in the denominator, we can evaluate the integral by partial fraction. Okay, so let us determine first the composition of the rational function 1 over x, x plus 4 into sum of partial fractions. Okay, and let me do it here. Okay, if we have 1 over x times the quantity x plus 4, since we have two distinct linear factors, then we can decompose this as sum of partial fractions a over x plus b over x plus 4. And if we will multiply both sides of the equation by the LCD x plus 4, then that will give us the left member equals 1 and the right member is a times x plus 4, okay, then plus b times x. And since there are two values of x that makes the denominator 0, if we will consider x is equal to 0, then that will give us 1 is equal to, when x is 0, then b times 0 will give us 0. And the first term is a times 0 plus 4, which is simply 4a. Therefore, this gives us the value of a, which is equal to 1 over 4. And the value of x that makes, the other value of x rather that makes the denominator 0 is x equals negative 4. So when x is equal to negative 4, then the first term here is 0 since negative 4 plus 4 is 0. Okay, and b times negative 4 is simply negative 4b. Okay, of course, the left member is 1, and this is equal to negative 4b. And if we will solve for b, then b is equal to negative 1 over 4. Hence, the rational function 1 over x times the quantity x plus 4 can be decomposed into sum of partial fractions a, okay, 1 over 4. Okay, so we have 1 over 4 over the linear factor x plus negative 1 over 4. So we can just make this minus 1 over 4 over the denominator x plus 4. Okay, hence, if we are going to evaluate this, then this will give us the limit, okay, of the integral of the differential of x over x times the quantity x plus 4, okay, from the lower limit 1 to the upper limit b. And after evaluating the integral, okay, we are going to evaluate the limit as b increases without bound. Okay, and since we have here the decomposition of 1 over x times x plus 4, then this is equal to the limit as b increases without bound of the integral, okay, from 1 to b of 1 over 4, since a is 1 over 4. Now we can just write it before the integral sign of the differential of x over x, then minus b is negative 1 over 4 minus 1 over 4 times the integral of the differential of x over x plus 4, okay, to be evaluated from the lower limit 1 to the upper limit b. And if we are going to evaluate both integrals, it leads to natural logarithm. Okay, and we might as well write 1 over 4, which are both present in the two integrals, no? We can write it outside the grouping symbol, and it is also equivalent to writing it before limit. Okay, so since it is a constant, so we will have the limit as b approaches infinity of, okay, integral to differential of x over x leads to the natural logarithm of x, okay, minus the integral of the differential of x over x plus 4 leads to the natural logarithm of x plus 4. And this must be evaluated from the lower limit 1 to the upper limit b. But before we evaluate the resulting indefinite integral within the limits of integration, we can use the third property, or rather the second second law of logarithm, second law of logarithm. We have difference. Okay, so we can express this as a single logarithm, no? And we have 1 over 4, okay, times the limit as b increases without bound of the natural logarithm of x divided by x plus 4, okay? Okay, and this will be evaluated from 1 to b. Okay, or instead of using the absolute value, we may use the parentheses. Okay, so to be consistent, let us just use the absolute value. Okay, so absolute value of x over x plus 4. And we're going to evaluate this from the lower limit 1 to the upper limit b. Okay, hence we will have 1 over 4, okay, times the limit as b increases without bound of, okay, for a while. So evaluating the indefinite integral at the upper limit b will give us limit of, oh, sorry, natural logarithm rather. Okay, we have natural logarithm of the absolute value of b over b plus 4, okay, minus the value of the integral at the lower limit 1. Okay, so we are going to replace x by 1. Okay, and that will give us natural logarithm of 1 over 1 plus 4. Okay, and if we are going to evaluate the limit as b increases without bound, then to evaluate the limit of natural logarithm of b over b plus 4, then we can divide both the numerator and the denominator by the highest power of b, and that is, of course, b, no? So that will give us 1 over 4 limit as b increases without bound of the natural logarithm of dividing b by b will give us 1 over dividing b by b will give us 1 plus 4 over b. Okay, minus the natural logarithm of 1 over 5. Okay, so this will give us, okay, if we are going to evaluate the limit, now we have 1 over 4 times evaluating the limit of loan of 1 as b increases without bound, no, is 1, okay? Limit of 1 as b increases without bound is also 1. And the limit of 4 over b as b increases without bound, of course, is 0. So that gives us natural logarithm of 1 over 1 plus 0 minus the natural logarithm of 1 over 5. Okay, and of course, we have 1 over 4 times, okay, 1 over 1 is of course natural logarithm of 1 minus the natural logarithm of 1 over 5. Okay, and since we know that the natural logarithm of 1 is 0, then we can express this as 1 over 4 times 0 minus the natural logarithm of 1 over 5, or simply 1 over 4 times negative natural logarithm of 1 over 5. Okay, but if you are going to apply the third law of logarithm, then we can express negative ln of 1 over 5 as ln of the reciprocal of 1 over 5. And the reciprocal of 1 over 5, of course, is 5. Therefore, this one is also equal to natural logarithm of 5. Therefore, the integral is equal to 1 over 4 times the natural logarithm of 5, okay? And we can now say that the given integral, the integral of the differential of x over the denominator x, x plus 4 from 1 to positive infinity is again convergent since the limit exists. So this is convergent.